Okay, so this problem says a long silver rod of radius 3 centimeter has a charge of minus 5 microcoulomb per centimeter on its surface. Okay. Find the electric field at a point 5 centimeter from the center of the rod and outside points, and find the electric field at a point 2 centimeters from the center of the rod. Okay, so so here's the rod, and the radius of the rod is 3 centimeters. We'll call it R0, 3 centimeters. And it's got minus 5 microcoulombs per centimeter charge. That's the linear charge density. Now we know that if you throw any charge on a conductor, it all resides on the surface. Okay, so the charge will be all on the surface. Okay. And we also know that for part B, the electric field at a point 2 centimeters from the center. So there is the center of the rod, and anywhere inside the electric field is 0. So for part B, we can answer that right away. Electric field inside is 0. So at R equal to, for R, any point R less than for R less than 3 centimeters, okay, electric field is 0. Okay. So now for points outside, so let's calculate the electric field here. Oops. The electric field will point inward because the charge is negative. Okay, electric fields point toward the negative charges. Okay, and what you'll find is the electric field is the same as so here I'm drawing a Gaussian surface. The electric field is like that, and so we will find the electric field at a distance r. Okay, and we are using Gauss's law, so the electric flux is equal to charge inside divided by epsilon naught, and here's the electric field. The top and the bottom surface of this cylinder do not contribute any flux because the electric field is from the symmetry is parallel to the surface. Only this portion contributes to the flux. Okay, and of course the flux is E dot A, this integral for this enclosed surface. Here's the cylinder, here's the top surface of the cylinder, here's the sides of the cylinder, here's the bottom of the cylinder. And only the sides contribute, and we'll say the height of the cylinder is h. And so the surface area of this side, the sides of the cylinder is 2 pi r times h. Okay. So this is equal to E dot E times 2 pi r h, and the flux is negative because the lines are going into the surface. The lines, oops. The lines are going into the surface, so the flux is negative. This flux is negative, and that's equal to the charge inside, And the charge inside is the linear charge density times the height divided by epsilon naught. Okay, and the linear charge density is 5 microcoulombs per centimeter. So minus E times 2 pi R H. Oh, the H cancels, so I won't write this H. Okay. And so the electric field is minus, well, okay. Now, okay, all right, I'll write the minus sign. So it's 1 over lambda over 2 pi epsilon naught 1 over R. And K, the Coulomb constant is 1 over 4 pi epsilon naught. So this comes out to 2K lambda by R. Okay. And lambda is, so lambda is, well, and lambda is minus 5 microcoulomb per centimeter. That's lambda. So there's the electric field. So the electric field is pointing inward, and the magnitude is absolute value of this, and it falls off as 1 over R. Okay. So anyway, the point is, for a conductor, as long as you're outside the conductor, this acts like a one-dimensional conductor, as a conductor with 0 radius. Okay. So once you're outside the conductor, the electric field is the same as if this conductor had no dimensions, if it was a thin conductor. Okay. All right. Any questions on that? Okay. Stop the recording.